Hey kids, time to begin Unit 8, Applications of Integration. Now, really, we did applications of integration at the end of Unit 7 too, with exponential growth and decay and logistic growth. But we also taught you some techniques, the separable differential equations, um, also an application of distance displacement and position, right? Using solving an initial value problem. So it's kind of unfair to label this unit just as applications of integration, but what can I say? That's what we do. So this is where Unit 8 begins. The first homework assignment is on a website. So I've put the link on Canvas. Here it is if you want to um, access it through the PowerPoint. And actually on Canvas, I also have a handout with the URL address and some directions, because if you just go to the website, you're probably not going to be able to figure out like what is it exactly that she wants me to do. And the nice thing about these website problems is it steps you through each of the problems, right? So how to set it up. The biggest issue with Unit 8 problems is the setup. You know how to integrate. You make a mistake here and there with integration, oh well. But you can't access the problem if you can't set it up. So the nice thing about why I like this website is that it talks you through and steps you through how to set it up. All right, so with that in mind, I want to remind you of stuff we did in Unit 5, which was where we started talking about the area and how the integral can give us the area as long as our function is above the x-axis. And then Unit 6 was actually how to do it, right? So Unit 5 was kind of like the setup and the concept, and then Unit 6 was the actual techniques of the integration, right? So I wrote this problem in a slightly different way than you would see it, but the reason I'm doing that is because where we're going. So if I just said find the area and I gave you this picture, and maybe even I called that area A, right? Now that this is a blown up picture of sine, so this is curved, right? Sine x. So, um, so if I did this, I would say what set up the integral for this area, and hopefully you would do this. The area, because the function is above the x-axis, the area goes from 0 to pi over 4, right? And x equals pi over 4 is this line, right? And you would say my x bounds were 0 to pi over 4, and I was integrating sine x with respect to x. And we kind of like ignore that, we put the dx, and if we don't put it, it's not that big of a deal. And we know how to do this with our calculator, Math 9. We also know how to do this by hand because we know the integral of sine x. And we could get this area. Well, look at how I've phrased it now. Between the x-axis and the graph of, from start to stop. So we've always kind of glossed over the fact that this equation, y is equal to sine x, is the first equation. We really do have a second equation. The second equation is y equals 0, right? Because on the x-axis, y is always 0. We really do have two equations. We really are finding the area between two curves, right? Where we have this strip here, and we have the top of the function is on sine x, and the bottom goes all the way to the x-axis. So in reality, I could write this integrand like this, right? Couldn't I? And wouldn't you get the exact same answer? But what I want you to notice is that inside this integrand, that's supposed to be a minus sign, is two functions, the top function and the bottom function. We just never had to think about the bottom function before because y was 0, Additive identity, sine x minus 0 is still sine x, so integrating sine x from 0 to pi over 4 gives me the same answer. So why am I going through all of this, right? You're like, okay, so that's swell. Great, Ms. Gans. But what's now going to happen, so you already have been doing the area between curves. It's just that the other curve was always the x-axis. You were always integrating from the x-axis up to a curve, got you true integral, down to a curve, got you an integral, wasn't true area because the function values were negative. So now I'm just going to move that. What if the second curve isn't the x-axis? And I want you to still find the area between the curves. That's where we're going. So look at this picture. Two algebra 1 curves, upside down parabola, linear function with a negative slope. Notice though that the intersection of these two algebra 1 functions creates a bounded area, right? Bounded. There is a concrete area. It's not infinite. So I could, if I wanted to find the area between these two curves, I could split it into several sections, but I would prefer not to, right? And I could use the properties of integrals and blah, 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 blah. But we have a way of saying, you know what? I want to draw a strip. And you are the click and drag generation. So I want you to imagine taking this strip and dragging it across the domain. Can you visualize that strip getting shorter and bigger and shorter again as you move through the domain from left to right? That's the idea of how to find the area between two curves. So here's just a nicer, prettier strip, but I want you to see and focus. So hopefully you're drawing this in your notes. The top of my strip is on the parabola. The bottom of my strip is on the line. And as I click and drag this strip through here, sometimes my strip is shorter over here. Sometimes my strip is very long, like here. Sometimes it's short again here. But as you move across the domain, you have a bunch of thin vertical strips that will cover the area between those two curves. So what if I just consider one of them though? The length or height of this curve, of this strip is top minus bottom. Be careful with subtraction. The top function, so let's pretend this y value is at 1. This x value is at 1. So the top would be 2 minus 1, which would be 2, would be 1. When x was 1, y was 1. And the bottom of this function, when x is 1, y is negative 1. What is the length of that curve? 1 minus negative 1. The length is 2, right? Of that particular strip. So this is an expression here for the length of any strip. Top 2 minus whatever your x value is squared minus negative x, subtract those two, and you get the length of the curve. Well, that curve, I keep saying the curve, the strip. Well, that strip also has a width now, doesn't it? So while I said this strip was at x equals 1, it actually has a little bit of width, right? So maybe it's 0.9 to 1.1, actually. That width we call dx, which is a small change in x. So what is the area of that strip? If its length is y1 minus y2, and its width is dx. Its area is length times width, which is length times width. That is the area of this one strip. Well, what if I want to draw this strip and find its area, this strip and find its area, this strip, this, I want to find them all, and I want to add them all up. I get the area between those two curves. What mathematical thing have you just learned that sums a bunch of products? Sums a bunch of products. The integral. Length times width. Add them all up. What are these two numbers? Well, remember, your width is in terms of x. Your function is in terms of x. These numbers must be in terms of x. Where did they come from? The points of intersection, right? You did that in Algebra 1. You said, when is 2 minus x squared equal to negative x? So when is x squared minus x minus 2 equal to 0? You factored. Right? That's where those numbers came from. That's freaking nuts. Now, if this is on a non-calculator portion of an assessment, which is likely because this is such a simple integrand to do, to evaluate, you could actually have to integrate this by hand. But the thing to note is that the top of the strip and the bottom of the strip never changed. No matter where you clicked and dragged this, the top was always the parabola, the bottom was always the line. The top is the parabola, the bottom is the line. The top minus bottom never changed. That's really important because the next example I'm going to do, that's going to change. Maybe foreshadowing. Think about what that would mean. Because the top and bottom don't change, I have one integral. One integral going from -1 to 2 because the strip never changed its boundary. So again, if this was on a non-calculator part, here's where the points would be. There would be a point for -1 to 2. There would be a point for the integrand. And then there would be a point for some of this work, right? Because you'd actually have to integrate. So there'd be a point for the integration. And then there probably wouldn't be any points, or maybe 1 point for the math, but probably not, of how you got to 9/2. And you don't have to simplify it. You could leave it as 27/6 or 9/2 if it's on free response. On multiple choice, 9/2 would be there. However, if this was on a calculator portion, +1 for the bounds, +1 for the integral, +1 for the answer. That's it, right? So make sure, do I have a calculator? Don't do the integration. Math 9 that baby. So here is one of the formulas for the area between two curves. Given that the top function and the bottom function never change from A to B. Also notice that this formula is all in terms of x. Which means you drew a vertical strip. Perpendicular to the x-axis. That's when you use this formula. So again, foreshadowing. There's another formula to come, so leave some space in your notes. So look at this example. Square root of x, algebra 1, x minus 2, algebra 1. I want the area between those two curves and the x-axis. So the area that I'm after, so be careful. This is the area that I'm after. Be careful with the words, because my answer would be different if they just said the area bounded between these two curves. Because after all, that one still goes down this way, right? So I would have to include all of that is the area between those two curves. But so the language of the problem is very important for your drawing. And I didn't even put the language up here yet. But what I want you to notice here is if you want to find the area between these two curves and the x-axis, my strips change. Top, bottom, top, bottom. The bottom function changes. The minute any of your bounds change, you have to change integrals. So look at what I did there. I found the x-intercept of a linear function. So as long as I was between 0 and 2, my top was the square root of x. And what's my bottom? Y equals 0. So I don't actually have to put the square root of x minus 0, right? But that really is there. But as soon as I had a strip that changed its bottom, I had to change the integral. From 2 to 4, my top function was the square root of x minus my bottom function. So this one was really top minus 0 because the 0 was the bottom. Right? Now, this isn't terrible, but it is more work. I have 2 integrals. So, but I could do this. Multiple integrals means multiple boundaries. And again, I didn't do this math, but I could, right? This is not devastating to do. I can do this, do my fundamental theorem, right? My integral evaluation theorem, right? This is x to the 1/2, so integrating that, x to the, right? You can do that. Or if you had Math 9, you would type it in and do it on your calculator. However, what if I do horizontal strips? If I do horizontal strips, notice when I click and drag this, the boundaries don't change. Boundary always on root x, boundary always on x minus 2. And again, the third boundary is the x-axis, which it would say in the words. So same space. It's the exact same space. But I don't want to do 2 integrals. I can just switch kind of the way I look at it. Now, I don't think top minus bottom. What do you think I think? Right minus left. instead of top minus bottom. That's all. And when you click and drag, you now need to look, instead of going from, right, 0 to 2 and then 2 to 4, which, by the way, I got the 4 from the point of intersection between these two, right? So now I need the same point. I have the same exact freaking point of intersection, but I'm going up and down the y-axis. How do you indicate that with an integral? Everything's in terms of y. Make that red to make it different. So if y is equal to the square root of x, I took algebra 1 and I paid attention. I can just square both sides, can't I? If y is equal to x plus 2, can I just add 2 to both sides? And now notice I have x by itself in terms of y. And I just was running out of room, so I made this on a different slide. Same information, right? I had y by itself. I got x by itself. And this time, I said not top minus bottom, but I said right minus left. Right was the linear, left was the curve. So inside my integral, I didn't do top minus bottom, I did right minus left. But I integrated with respect to y, so all my functions are in terms of y, and my bounds are in terms of y. Remember, this point of intersection was 4, don't care, 2. When I was integrating with respect to x, the point of intersection was 4, don't care, 2, right? Everything has to be, your strip is looking at the y-axis, right? Length of the strip is right minus left. Width of the strip is now a little change in y. And my bounds are y numbers. Now, this also I could integrate by hand, right? This is not hard to integrate by hand. And I got 10/3, which is exactly the same answer I would have gotten had I integrated with respect to x and integrated root x and integrated root x minus 2 and plugged in 0 and 2 and subtracted to the first integral and 2 and 4 to the second integral and subtracted. I would end up with 10/3 if I'd made no mistakes. Do be careful when you are using your calculator. If I had a calculator and I would be math nining this, right? Your calculator, you can't, just lie to your calculator. Tell your calculator these are x's, right? But you're going to put x plus 2 minus x squared. Yes, you're going to, right? Shh. I know you're lying. The calculator's a machine. It doesn't really know. You feel a little guilty, but your calculator will spit out 10/3. So, before I want to do that. Sorry, I want to go back. So, the general formula, remember I told you to leave space? So, the area, if you want to integrate dy, in general, is the integral of g in terms of y minus the second one in terms of y, dy and we'll call these C and D, but they're Y numbers. And what you want to think is, instead of top minus bottom, you do right minus left. But it is important, if you're going to integrate with horizontal strips, which is perpendicular to y-axis, everybody has to be in terms of y. So my general strategy, sketch, right? If you don't have a calculator, sketch, and it's going to be one of your functions that you learned in Algebra 2, right? A general exponential, general trig, general log, general, right? If you don't have your calculator, you are expected to be able to graph those curves and find any points of intersection. But it will be simpler, Algebra 1, Algebra 2 type ones. If the functions are more complicated, you'll have your calculator. But make sure to adjust your window so you can see the area you want. Then this is your thinking step. That's a light bulb. It's a really poor light bulb, but it's a light bulb. Decide. Decide, should you do vertical strips, top minus bottom, or horizontal strips, right minus left? Pick what's easier. Sometimes you are being tested on your decision-making process, and this is one of them. Maybe they tell you which way to do, but they probably won't. And then you decide which way to do it. And if you pick the longer way, because you're like, I only know one way to do it, I'm only going to do dx, I'm only going to draw vertical strips, and you end up taking too long because it's a longer process, or you make silly mistakes because there's more steps in that one, more integrals, that's on you, right? And don't be saying like, oh, the test was too long. No, you're being tested on not only your content, but your efficiency and fluency with the content. Then you write an expression for the area of the strip. So that is either top minus bottom is your expression, or right minus left. Don't forget to match your variables everywhere in the function, in the bounds. Find your limits of integration. Remember, the limits must be x if you have vertical strips, y if you have horizontal. This is often, it is either given to you, or you find the intersection with algebra if you don't have a calculator, or if you do have a calculator, with that second trace intersect feature. And then integrate. Most of your points come here, the setup of the integral to find the area. Because if you set it up wrong, you make a mistake, right? You have the y values instead of the x or whatever, you still get credit for your answer as long as they see your setup, right? You'll get dinged on your setup if your setup is wrong, but you'll get follow-through points on your answer. So let's do this example. And I tried to highlight a couple different ways this could be asked. So find the area of the region bounded between. So these two functions, secant squared of x, which is right here, and sine x do not intersect. So you cannot find points of intersection. They don't meet. However, they asked for the area of the region bounded between. These are vertical lines at x equals 0, and a vertical line at x equals pi over 4. So that's 3-ish divided by 4, so around 1/4. I'm sorry, 3/4. That's this line. Here's the curve sine x. Here's the curve secant squared. So do you see the area bounded between there. There's no points of intersection. The two functions don't meet. They gave me the bounds. Should I do verse? So step 1, sketch. Step 2, decide. Should you do vertical or horizontal? What do you think? Well, let me tell you a clue. They've given me functions in terms of y, and writing these functions in terms of x would be a little devastating, right? This would be x is equal to inverse sine of y, x is equal to inverse secant square, whatever. Also, the bounds they gave me were x numbers. Now, it's not to say that 100% of the time that they give me a function this way, I can't change everything, but not with these functions. So that's already a clue that pretty sure I'm going to be drawing vertical strips. So step 1, sketch. Step 2, decide. I decided vertical. Since I decided vertical, that means I'm going to integrate with respect to x. So when I integrate dx, that means everything in here, that means I'm going to be doing top minus bottom, and that these are going to be x numbers, and that my function is going to be in terms of x. So what do I have here? Who's my top? Who's my bottom? Is everybody in terms of x? Check, check, check. Oh, what about these? There's no points of intersection. Where are these numbers coming from? Where are you starting to draw strips? They told me x equals 0 to x equals pi over 4. Start drawing strips at 0. Stop drawing strips at pi over 4. So my limits of integration in this one were given to me. Right? So now I'm going to actually integrate. If I can do this one without a calculator or with, really, right? Let's pretend I didn't have a calculator. If I don't have a calculator, then I would actually use the property of integral and integrate secant squared. But what is secant squared? The integral of secant squared is just what? Tangent x minus the integral of sine x, which is what? Negative cosine x. So I have tangent of pi over 4 plus cosine of pi over 4 minus what? Tangent of 0 plus cosine of 0. So 1 minus 1 goes away, this 0 goes away, and I just get root 2 over 2. If I had a calculator, remember, you don't have a secant button on your calculator. So you have to, right, you have to do 1 over tangent all squared minus. So this is why if I did have a calculator, I would actually put 1 divided by tangent x squared into y1 and sine x into y2. Make sure you're in radians. And then I would math 9 y1 minus y2 from 0 to pi over 4. And you'll get 0.707, which is root 2 over 2. One more. Look at how I wrote this one. Find the area of the region between. I didn't give you any bounds. So that's kind of a clue that I'm going to need to find points of intersection. So x equals y to the 1/3 is really the cube root of x, right? Y is equal to the cube root of x. And this is a parabola that opens the wrong way, that is righty-lefty. I learned that in Algebra 2. Coefficient on y squared is positive, so it opens to the right. Minus 2 means the vertex is at -2. So there I go. So step 1, sketch, done. Step 2, decide, vertical or horizontal, right? Can you see the issue here with drawing vertical? Right, if I were to draw a vertical strip, top minus bottom, well, that's a pain in the butt. How am I going to do that? Well, and then I got to do this, right? And then the bound change, ooh, right? Annoying. So how about I do horizontal strips? Look what happens if I do horizontal strips. No matter where I draw the horizontal strip, the right and the left bound stay the same. Another clue. Look how they gave the functions to me. So I sketched, I decide I'm going to do horizontal, sketch and see, decide, I decided horizontal strips. Horizontal strips are perpendicular to the y-axis, so that means looking at y. I see you, y. Now set it up. Integrate dy. But this time do right minus left. Who's the right function? The furthest right. Is it the cube or the parabola thing? It's the cube root, right? So y to the 1/3 is the furthest right. The left is y squared minus 2. Be careful with those subtractions. dy. Yes, y, yes, y, yes, y. So these numbers have to be y numbers. Now look at my drawing. So I found these points of intersection for you, but I purposely made, and I wanted to put up here the full coordinate. You're integrating with respect to y, so which values do you want? You're going down to up through the domain, right? For your strips start farthest down, that's a -1, and then farthest up on the y-axis. You want the y coordinate. So my y values are, my lowest y value is -1, and my highest y value to 3 decimal points is 1.793. And then I just pop this into my calculator, right? I would have a calculator because that intersection point is not nice. They're not expecting you to do the algebra to solve for that. And I got 3 places past my decimal. At least. You can put more, but you can't put less. So if this was on an assessment, the points would be, no one's going to give you points for your drawing, but the drawing helps you. The points would be for your bounds, for your integrand and your answer. And if you make a mistake with your bounds or your integrand, your answer will get follow-through points as long as they can tell what you did. Okay. In our live session, we'll talk a little bit more about some shortcut, some shortcut keystrokes where you can store these values. Some of you already know, but you can store values in your calculator directly from your graph screen, both the x and the y coordinate, right? So we'll talk a little bit about that, and really, whether you'll be tested on integration when you're doing application problems. The vast majority of the points are in, did you recognize what to do with the problem and did you set it up right? That's where most of your points come in. So we'll talk about that more in our next live session.